Hi, we're the University of Maryland's 2024 Big Idea Challenge team. The Space Systems Lab's primary interest is in robotics, so when we saw the challenges focus on inflatables, we thought a lot about how on Earth we could possibly apply inflatables to planetary surface robots. The majority of planetary surface robot wheels are rigid because it's easier to make them wear resistant like that. However, rigid wheels, when encountering loose terrain, spin, excavate, sink, and then can get stuck. Flexible wheels can help with that because they deform, so they have a larger contact patch, spreading their weight out more evenly and also gaining some more traction. Our concept is to combine flexible wheels and rigid wheels together with an inflatable that deploys from a rigid wheel. So to see exactly how well that concept works, we've iterated through a bunch of different wheel designs, deployment systems, and retraction systems. And then we built a whole experimental setup in order to quantify the difference in performance between all of those.
Previous work with inflatable rover wheels showed challenges with wear and durability. So we designed a Viper or Lunar Resource Prospector class rigid rover wheel capable of containing soft goods and deployment mechanisms inside for a self-contained, remotely inflatable hybrid rover wheel. Some wheels had deployable grousers. Others didn't. We even varied the kinds of deployable grousers to find patterns and mechanisms that worked best, utilizing the grouser retraction as a way to deflate and restow the inflatable inside, even in low pressure environments.
The inflatables themselves are made of two different fabrics. The pressure bladder is made of a polyurethane coated nylon, hand heat sealed around the edges to create an airtight seal. The restraining layer or restraint layer is made of 500 denier Cordura fabric with grommets added along the edge for securing of the retraction method. Heat sealed pressure bladders come in various shapes and sizes, determining what their different uses are. They come from the smallest design to a largest design used in our inflatable wheels that are manually inflated to a medium size, which is housed in our CO2 inflatable wheel.
And so to test our inflation and retraction systems, we made a wireless inflation control system that allows us to inflate and deflate the wheel with a wireless remote. And so you can see it's inflating right now. We can stop it, we can restart it, and there's an internal regulator that keeps it from going too high pressure to prevent it from bursting the pressure bladder. Now, this system runs off of 16 or 25 gram prepackaged CO2 cartridges. It features an inbuilt pressure regulator, pair of solenoids, and all the associated plumbing and electronics to run the system. All of this is contained entirely within the hub of the wheel, leaving nothing exposed to the lunar environment. While you can hear it inflate, you will not be able to hear it deflate in this case, other than the action of the solenoid, because we don't have the spring-loaded pedals currently installed.
So reliably retracting the inflatable has been a significant challenge throughout the course of this project. The first way you think of retracting an inflatable on Earth is just to hook up a vacuum hose, sucking the air out from inside, and then atmospheric pressure does all the work to push it back in. But on the moon, obviously we have a vacuum on the outside already, so a vacuum on the inside isn't going to help us retract the system. We thought about actuated methods of doing this, but we didn't want to add more complexity to the system or have more points of failure. So we've come up with a fully passive system for retraction. We have springs in the hinges of these pedals and also springs on the tips of the pedals that all work together to push the inflatable fabric back into the wheel. The thing that lets us repeatedly compare the performance of our different wheel designs is this linear wheel test rig. Each of the wheel designs gets mounted into the wheel test rig and driven across the soil. While we're driving, we track forces and torques of the wheel, while also looking at the sinkage that the wheel experiences as it's driving. By driving the horizontal differentially to the wheel drive motor, we're able to create our own distinct slip values. We also manipulate the weight that's on the wheel in order to simulate proportionally larger or smaller rovers. But between each test, we loosen the terrain and then smooth it in order to get a consistent level ground.
In order to support testing all of our various wheel designs, we made a lot of upgrades to our wheel test rig. Our wheel test rig now runs ROS 2 and features a Galil card for enhanced servo control of the horizontal system. This allows us much greater precision and greater data acquisition capabilities than we had before. All of this gets combined into one amalgamated log file and then gets processed to determine the efficacy of any wheel that we put on the test rig. One of the really important tests for us was to see if our technology could deploy and retract under vacuum conditions. So we've taken our wheel, put it inside our dirty thermal vac chamber that we have on premises, and we've attempted an inflate and deflate cycle to see how well the springs compress the pressure bladder under vacuum conditions.
Additionally, we worked to upgrade an existing small-scale rover in our lab to support the tests of these wheels. And this 4-wheel rover test bed is able to demonstrate recovery from conditions where purely rigid wheels became stuck.
The other wheel is flipping, this one isn't. Oh.
We would like to thank the NASA Big Ideas team for making this opportunity possible for us, as well as NASA and Maryland Space Grant for the funding involved in this project. And we would also like to thank all of the people on our team that are not appeared in this video for all the support and work they've done on this project.
Thank you.
Thank you.
Thank you.
Go.
Nice.
Thank you.